In this video, we'll be going through our carbonyl compounds. So our carbonyl compounds, as mentioned before, have this C double bond O character. If they have hydrogen and an R group, they are then aldehydes. If they have two R groups, they are then ketones. Aldehydes have the ending of Al. Ketones have the ending of ONE. So, if we had a compound that looked like this, CH3, CH2, C, double bond O, and then H, this would be 3 carbons plus an aldehyde, giving us the name of prop and Al. Now, for a ketone, because these are R groups, the carbonyl group has to be in the middle of the chain. So, if we had CH3, C, double bond O, CH3, there are 3 carbons, so we know it's prop, and the ketone's in the middle, so we know that it's propanone. Now, for this molecule, we do have to use the numbering for where the ketone is located. For aldehydes, they always have to be at the end of the chain because this hydrogen needs to be there, so no numbering is necessary. For propanone, there's only one location that the ketone can be in, but for other compounds, for example, this structure has 1, 2, 3, 4, 5, 6 carbons. There are 4 places where that ketone could be, so numbering is necessary. So for example, we can call this 2-propanone or just propanone because there's really only one carbon where that carbonyl group could be. So most of the reactions for ketones and aldehydes we've already gone through given our oxidation and reduction tables. Another set of reactions that you need to know are the oxidation of aldehydes to carboxylic acids. So you're going from aldehydes and oxidizing to carboxylic acids. Now remember, this is not with ketones, this is just aldehydes. There are 3 types of reagents that you can use. So the first would be the Phalen's test. The second would be Benedict's. And the second would be Tollin's. What these 3 do are used as diagnostic tests, which convert aldehydes into carboxylic acids. So for example, if a ketone were present and you use these 3 tests, no reaction would occur because you cannot oxidize a ketone. These only work with aldehydes. The second reaction that was gone over in class were the reactions of hemiacetals and full acetyl reactions. So we go from an aldehyde to our hemiacetal to our full acetyl. Now there's a very easy way to think about this. We start with an aldehyde. Let's make it simple. CH3, CH2, C, O, H. So the first step to making that hemiacetal compound is to add 1 mole of an alcohol. So if you add 1 mole, you go to the hemi. If you add 2 moles of alcohol, you go to the full acetyl. So if we add 1 mole of alcohol, let's pick another simple one, CH3OH. This is the first mole. Let's see what happens. Now, there are 2 places where this could go. In a carbonyl structure, the carbon is less electronegative than the oxygen, and that we had learned in Chem 100 and Chem 101. Electronegative is the property of electron sharing within a bond. If oxygen is more electronegative than carbon, more of the electrons are going to be pulled towards oxygen, making oxygen act negative and carbon act positive. Same thing in this alcohol. The oxygen will act negative and the hydrogen will act as a positive. So if we label our groups once again, on the carbonyl, the carbon is positive, the alcohol or the oxygen is negative. So when we do this reaction, this oxygen is going to attach to this carbon while the hydrogen goes to the oxygen. So our final product will look like such, as such. So what can we see here? We have an OH group and an OR group. When you have one of each, it's called the hemiacetal. Now we have to go to the full acetal. What happens now is we then take this reaction and we then add the second mole of our alcohol. And once again, let's not forget about our charges. The oxygen is negative, the hydrogen is positive. So now we want to look at this bond. The oxygen here acts like a negative, and the carbon, once again, acts like a positive. So the easiest way to remember this is that when this hydrogen goes to this oxygen, water is made. Right? H2O. When H2O is made, it's just going to leave the molecule, and this second group is going to come in and attach to that central carbon. So when that happens, our final product looks like this. And this is our full acetal. And you can notice that there are two OR groups giving the full acetal, as opposed to earlier when there was only one OR group and one OH. So we can see that when we added this hydrogen to the OH group that was already existing, we created water, and water left the molecule. Then we left this positive carbon open, to which this methoxy group, this OCH3 group, attached, giving us our full acetal.